Hello. Hello. Good morning to everybody, and thank you for being here. Well, it is a pleasure to have here Dr. Peter Wisinovic. He has been the head of optics and adaptive optics in the Keck Observatory, the two Keck telescopes in Hawaii, for decades. And the Keck telescope design and development was the reference for the GTC. And those two telescopes have been producing science with adaptive optic systems for many years. And it's a reference that we have to follow. So yes, I give the word to Peter.
Buenos días. Me encanta de estar aquí con ustedes, pero mi español es demasiado pobre para hablar. Y ahora necesito hablar en inglés. Disculpe. Lo siento. Okay, so it's a pleasure to be here. And thank you very much to Marcos for inviting me. So I'm going to talk to you about the Keck telescopes and adaptive optics at Keck. And this picture here is actually a picture of the two laser guide star adaptive optic systems at Keck observing the galactic center. Okay. And I'm not getting any response here. Okay. So the outline of the talk is I'll talk first about the telescopes and give you an overview of the telescopes and adaptive optic systems, then give you a little feel for the science that is being done with the Keck adaptive optic systems. And then I'll get into the development activities, which are based on our performance, basically. And so we're going for a higher sky coverage system with, using laser tomography with the COPPA project. We're pushing on the other telescope for visible and high contrast science. With the HACA project, we're also working on a bunch of advanced wavefront control techniques. And we're also looking at basically a satellite with a source for adaptive optics. And then I'll end with the Keck Scientific Strategic Plan for 2035. So in terms of an overview, first of all, I'm not sure how many of you are familiar with Maunakea. So up on the summit of Maunakea, there's quite a number of observatories. You can see we're on a volcano like you are. You can see the shadow of the volcano on the clouds there, also below the mountain. And the two Kecks are in the center there. And then to their right is the Subaru telescope. Oops, that's what I was afraid of. So there's 4 8 to 10 meter class telescopes, the two Kecks, Subaru telescope, Gemini telescope, and then there's a number of 4 meter class telescopes, Canada France Light telescope, NASA facility here, also United Kingdom infrared, and then there's a bunch of sub-millimeter telescopes down here in the valley. And if TMT ever happens, it'll be in the foreground right down in this area. So this is not the GTC, this is the Keck telescope. You can tell because the mirror is a little smaller. And so GTC is always tries to impress with 10.4 meters, we're only 10 meters. So we've got a number of instrument ports on the Naismith platforms. On the left side is a shell spectrograph, and on the right side there is the Keck adaptive optics system. And then we can also have instruments at Cassegrain or folded Cassegrain. And these are some of the seeing limited instruments. So there's a total of 4 seeing limited instruments on Naismith platforms. There's 3 that can go at Cassegrain, and there's 1 that can go at bent Cassegrain. And these are a mixture of mostly spectrographs and a lot of multi-object spectrographs, that kind of thing. I'll talk to you more about the adaptive optics systems. So our support system for the segments is similar to GTC. We basically have 3 actuators that tip, tilt, and piston the segments. We have capacitive sensors around the edges of segments to allow us to sense the piston between the segments and control the primary mirror phasing as a function of elevation, temperature, those sorts of things. And then each actuator breaks out to 12 contact points with the mirror that support the mirror at zenith. And then there's a radial post at the center of the segment that supports it at the horizon. And then we measure those segments in the telescope. And this is basically an image from a Shack-Hartman camera there. And from that, we measure the segments, and then we warp the segments in the telescope. And basically there's warping beams, these leaf springs that you can see here, here, that apply a force to the front of the mirror. So we measure the segments and change their shapes once they're installed in the telescope. And we just do that once after a segment exchange. And then to control the pistons of the segments, there's basically an aperture across the boundary between two segments. And you're basically looking for constructive interference between the two. And you start with narrow band filters until you get closer, then you use broader band filters. And so when you're in phase, you get the image at the top. And when you're halfway out of phase, you get the image at the bottom. And so we just piston the segments, look, through a series of steps, determine the phase, and then have the segment stays to about the 20 nanometer level surface initially, but that can fall apart a little bit with time to maybe more like the 100 nanometer level. So why do adaptive optics? Traditionally we've just been building larger telescopes to collect more light, and your sensitivity increases with the diameter of the telescope. But the goal of astronomical adaptive optics is so you also get the angular resolution of the telescope, and the bonus is you also get another factor of d squared in terms of sensitivity for point sources. And the images on the right there is an image of Neptune, where you're limited by the spatial scale of the atmosphere or not. And we get maybe, Neptune's about 2 arc seconds in diameter. So you're getting about 4 resolution elements across that. And then in K-band, when we close our loop, we're getting more like 20 resolution elements across Neptune. So there's been a lot of studies of the weather on Neptune, that sort of thing, with Keck AO. This is one of our Keck adaptive optics benches on the Keck 1 telescope. And then the green instrument beside it is OSIRIS, which is an integral field spectrograph. And all the electronics are on the other side of a wall. That's why you see all those cablings, all those cables going through the wall to the electronics racks. And then this gives you a feel for the optics on the AO bench. So this is about 2.6 meters in diameter. So the light comes from the telescope through a K-mirror rotator, which can allow you to keep either the field or the pupil fixed. So for high contrast observations, for example, we use it to keep the pupil fixed. This has already died. A fast dip tilt mirror next. And then an off-axis parabola, which collimates the light and reimages the primary onto the deformable mirror. We just have a 349 actuator deformable mirror. Then another off-axis parabola here, which is your camera that reimages onto either the NERC2 instrument at this port here, or another instrument at this port. And then the light that's reflected off an infrared dichroic here, the light that's transmitted is in the infrared. The light that's reflected goes over here to our Shack-Hartman wavefront sensor camera that we can use for either NGS or laser guide star wavefront sensing. And then the light that's reflected, I can't really point very well here. The light that's reflected off another dichroic here in laser guide star mode goes to a tip tilt sensor and a truth wavefront sensor, so we can correct for the aberrations introduced by the laser itself. And then we also have a visible camera, ORCID, over on this side, a fast visible camera and an acquisition camera. We also can have a wavefront sensor over in this area. We also feed a different instrument, KPIC, at that location, which is a single mode fiber. So we're basically at that point putting exoplanet light down a single mode fiber to a spectrograph with a resolution of about 35,000. So science, that's the whole purpose of adaptive optics on our telescopes. These are the science capabilities. The items in green are the current capabilities. So on Keck 1, we have the integral field spectrograph OSIRIS, which also has an imager. On Keck 2, we have a near-infrared camera, NERC2. We have a near-infrared spectrograph, which can be we can feed the AO system to its slit. And we also can feed NIRSpec with a single mode fiber from the Keck Planet Imager and Characterizer. And then we also have that visible camera, ORCID. And then the items in yellow are the items we're working on right now. So we're working on the upgrade for a laser tomography system on Keck 1, and we're hoping to get a better integral field spectrograph, LIGR. And then on Keck 2, we're replacing the 349 actuator deferral mirror with a 2844 actuator DM. That's a HACA project. And longer term, we hope to have an infrared wavefront sensor to go with that. And then 2 instruments are being built for that system. Scales, which is a 2 to 5 micron integral field spectrograph, and high spec, which is a single mode fiber, being a R of 100,000 spectrograph. And these are just the instruments that are in development then. Scales, which we hope to have the end of this year. High spec, which we hope to have later in 2026. And LIGR, a little bit less known, but it's actually gotten through its final design phase. So in terms of science productivity, this is the total number of, or the cumulative number of rough read science papers published using data from the Keck AO systems. So a total of, through the end of 2024, a total of 1,361 rough read science papers distributed in these kinds of categories. And you can see some breakpoints. One is here where we added our laser guide star system. So now we're able to do things like extragalactic science much better. And then another breakpoint here when we started to do a lot more exoplanet science, both largely because of now having techniques to image exoplanets, also following up from space observations, and also our Keck Planet Imager and Characterizer. I used to also keep track of the number of LGS-AO papers worldwide, rough read science papers using LGS-AO. The first papers were back in 1995 using this Starfire optical range telescope. And then nothing really happened until the Keck system turned on and started doing science in 2005. We pretty much dominated laser guide star adaptive optics for quite a while until the VLT, I'm going the wrong way. Until the VLT, that orange bar, that's the VLT AO facility. And it's mostly ground layer AO, but it also does laser tomography. And I sort of lost interest in tracking this thing because VLT was going to dominate again. So another way to track the metrics here is, this is a list of the top 10 cited papers that use data from the Keck AO systems. One of the particular note is Andrea Ghez. She and Reinhard Genzel got the Nobel Prize using adaptive optics, observing the center of our galaxy. So that's a highly cited paper. Christian Marois also did, the nice imaging of multi-planet systems with HR 8799. But also of interest is the first paper there is actually constraining dark energy. And the fourth paper is using dark matter to constrain H0. So I really like these gravitationally lensed kinds of observations. There's a lot of great physics coming out of those. So I just took some pictures from 2023 to try to illustrate the various types of science. So there's a lot of solar system science. This happens to be photometry of some of the fainter moons of Uranus. So they can do photometry of those. This is, again, those HR 8799 imaging where we've been following the orbits of these 4 planets. And we've also been able to make wind speed measurements, basically. And so we're seeing that the minimum wind speed, at least on these planets, is about 10 kilometers per second. Okay, it depends on the orientation, of course, with respect to us. So, and then I just like this picture of the Orion bar measuring the H2 regions. It's just a pretty picture. Well, of course, there's science there too. And then here's one of the galactic center images where they were actually looking at this X7 source that's being tidally disrupted, basically being destroyed as it comes close to Sagittarius A, the black hole. And then an example of the gravitational lensing of galaxies, and you're able to characterize both dark matter and dark energy with these observations. So, the astronomers are never satisfied. So, they want more out of our adaptive optics system. So we're trying to understand what limits our science and, what do we do next? And so that's the source of our developments. We've basically produced, an adaptive optics error budget here, in this case for the laser guide star, These are all the terms greater than 30 nanometers. We've anchored it to on-sky measurements, both of engineering stars and galactic center observations. So we can reproduce those in our error budget. And so we've used that as the basis for our current development activities. So we've upgraded the real-time controller systems to deal with the bandwidth error, but also to allow us more flexibility for adding new capabilities like Kappa and Haka. So we needed more powerful, computers. We've been using advanced, and that deals mostly with the bandwidth error, but also, again, provides us with a better platform. And then advanced wavefront control, we're using that to mostly help us control piston errors in the primary mirror right now, but also things like predictive control. And the Kappa project is helping us to, where we're projecting multiple lasers, allows us to deal with the focal and isoplanetism error, the fact that, well, I'll show you a picture of that in a bit. And then Haka is just a higher order deformable mirror so that we can reduce the atmospheric fitting error and also reduce the errors in the primary mirror as well. And with Kappa also, we can improve the tip tilt because we've got a near-infrared tip tilt sensor with it. So this is focal anisoplanetism. This is the biggest error term in our error budget for laser guide star. It's the fact that we're sampling a cone of the atmosphere, but the starlight or the science light is coming through the cylinder. So instead of projecting a single beacon, we're projecting multiple beacons to sample that whole cylinder of light. And this is a layout of that system. So far we've implemented all the hardware, but we haven't started demonstrating this on Sky at all yet. So we've got a new laser and laser table enclosure. We've got an asterism generator up near the top of the telescope where we project a center launch system, the new real-time controller, a bunch of new asterism simulator, a precision calibration unit, a telescope and turbulence simulator, so we can demonstrate everything during the day, demonstrate all our closed loop interactions and do all our calibrations, the new wavefront sensor, and then also the near-infrared tip tilt sensor. We're trying to improve its performance. So this is just pictures of the hardware. When we're mounting the new laser, it's the same optical laser that you're going to be using at GTC. New real-time controller, the interface to all our existing hardware, new wavefront sensor, and this allows us to have I've mentioned projecting 4 laser beacons. Well, we have to sample all 4. We put all 4 pupils basically on the same camera, okay, on a radius of 7.6 arc seconds. And then this is just some demonstrations of performance on a science target on the top, and just that we can also go fainter with our new wavefront sensor system in RTC. And then a bunch of simulators. In particular, this is how we have LGS fibers here, NGS fibers down here. They combine them, go through a wind screen, basically, a phase screen that we can move across so we can simulate winds up to 10 meters per second. Then through a pupil stop that looks like our primary, and then through the K mirror into the system. So, and that's the sample of our phase screen that we're using for those demonstrations. And then this is our asterism generator, and you can see the 4 LGS that we project on the sky here on our acquisition camera. And those are just ghost images because of our acquisition camera. And then we also, of course, have to work on the real-time control part, the reconstructors, all that. So we've got new algorithms for laser tomography in this system. We've got a bunch of new prediction tools, both the error budget I showed you before, but also an OMAO physical optics model that can tell us Strel versus position, or full width half max versus position in the field, or in squared energy. Our science team has been working on, actually have delivered new public data products that all astronomers that use Keck AO or Kappa can use: exposure time calculator, Strel calculator, data reduction pipelines, distortion solutions, and still working on things like point spread function reconstruction. And we're also working with them on improving the performance of our tip tilt sensor. This is a tip tilt sensor. It's an H2RG detector. So we've got a 100 arc second field of view on that. We can pick out any star in the field and read out 4x4 pixels there, and just multiple reads to reduce the noise. And you can see this is our visible tip tilt sensor's performance versus the near infrared tip tilt sensor performance. So this is on an integral field spectrograph, so you don't see a lot of resolution here, but you can certainly see the error ring. HACA, we're replacing the existing deformal mirror, exactly, just pulling it out and putting in a new deformal mirror from Keck AO, which will have 2844 actuators. So our fitting error will be greatly reduced. And that's for, we want to move towards the visible, but also do better high contrast observations. And this is just curves of the HACA performance. So the red is basically how we'll improve performance when we have bright stars. And then, but it doesn't hurt our laser guide star performance. The dashed lines show laser guide star performance. So we'll continue to improve that performance. And then with HACA, we'd like to add an infrared wavefront sensor. We have the camera, but we don't have the rest of the system or funding for it yet. But the idea of using an infrared wavefront sensor, in this case would be a high order pyramid wavefront sensor, is many stars are M stars, they're pretty red. And they're also, because they're behind the AO system, that's a diffraction limited core that we'd be moving around the tip of the pyramid to do our wavefront sensing. And the plot on the bottom, our science team produced, which shows basically contrast versus angular separation. And the light solid line is what we expect with just the high order deformal mirror. And the dark solid line is what we expect to get with the infrared wavefront sensor. Those are a performance prediction. And for reference, the dashed line is JWST. So we should be able to get higher contrast observations of these M dwarfs that host exoplanets with this high order wavefront sensor. In terms of advanced wavefront control, we've been working on a number of techniques to improve our primary mirror phasing. That's because the edge sensors that we use with our phasing camera only sense the edges of the segments, right? But if you can have other techniques, you can interfere the entire segment and get the optimal phasing. And also it may change with time or things like that. So we've tried, doing it with pyramid wavefront sensing. We've tried to do it with focal plane phase diversity, but the technique we're settling in on is Zernike wavefront sensors. And here the idea is, this is, well, Zernike wavefront sensor, actually the folks at LAM developed this, but we've got our phase screens from JPL, and they're metasurface screens, and they can actually put two different metasurfaces on there, and they have different phase shifts with respect to each other. And so they have, Zernike wavefront sensor is probably the highest sensitivity wavefront sensor you can have, but it doesn't have much range, right? And so this allows us to have two different ranges, and you use with two different polarizations. You put that then on two pupil plane images, and the result is shown here. Those two pupil plane images are shown on the top left, and you can see the phase discontinuities a bit with the segments. And then in the center, you can see the actual measurements from that of the pistons between segments. And then when we applied those errors to our active control system of the primary, we got the pupil images at the bottom, so much better phase. And then you can see the result on the right. That was the Strel ratio at K-band before our correcting the primary with Strel of 57%. And then we gained 10% in Strel after phasing the primary with the Zernike. We've also been working on other focal plane wavefront sensing techniques. This is a technique called Fast and Furious, which just uses focal plane images from your science camera, and then also uses the information of between exposures of how you controlled your deformal mirror. So it gets basically the sign of symmetric aberrations. And this is some examples of in the pig frames, getting a K-band Strel of 44% on the laser guide star, or when we were using laser guide star AO, and then improving that to 57% after multiple iterations for the laser guide star system. And then we can also use it on binary systems and improve the performance. We've also been looking at speckle nulling, which a lot of groups are working on for exoplanets, and just have demonstrated being able to dig a hole by applying aberrations basically to the deformal mirror to dig a hole in a particular area where you might want to look for an exoplanet. And we've also been working on predictive control. So basically from the past recent history, then predict what the next correction should be. And so improve your correction that way. And you don't see much improvement in terms of Strel, but you do see improvement in terms of contrast. And this is showing, a factor of a few improvement in contrast using predictive control. So a whole other approach is, you use laser guide stars for high sky coverage, but you still need a natural guide star. A whole other idea is produce your own natural guide star far away. And so the idea here is to use a source on a satellite in a very elliptical orbit, something like 200,000 kilometers at its extreme. And at its extreme limit, then, it's basically stationary with respect to your science target, or within a few arc seconds for extended periods. And then you can also do sort of serendipitous observation as well at other points where it slows down with respect to the background sky. And basically with this technique, if we had a satellite, of course, you're only able to do this for a few hours every 5 nights or something if you have one satellite, because you have to change your orbit for the next target. But you can really improve the performance because you've got a 0 magnitude natural guide star in front of your science target. And we've been doing risk reductions for that. We first implemented a fast visible imager just to make sure that as we went to the visible, that we would actually get diffraction limited images. And this image of theta Ori C at 650 nanometers is basically we're demonstrating 15 milliarc second full width half max. So we know we can actually achieve good. There's no STREL here. It's very poor STREL, but we actually can get a diffraction limited image in the visible. We've also demonstrated, a target, a source, a natural guide star, if you like, using an asteroid passing in front of a galaxy. And that we could close the loop on that guide star and correct the galaxy in the background. And so we've got this whole list of A pulses or asteroids where we can observe targets in the background. And we've observed some of those. And we demonstrate we can get good correction by taking short exposure images and then combining them later, right? Just stacking them. The third thing we've done is we use the laser communications relay demonstrator, which is in a geostationary orbit. And we just pointed our telescope at it. And they pointed their lasers at us. And in the image on the bottom right, you can see when we had an open loop, we're basically getting a seeing limited spot. But when we close the loop, we're actually getting a diffraction limited image. This was with our infrared wavefront, pyramid wavefront sensor. So we've demonstrated we can communicate, we can collaborate with a space asset and plan our observations and actually carry out a successful observation. The next thing we need to do is implement tracking field steering mirrors, because our problem is our wavefront sensor, or our guide star in this case, is moving with respect to our science target, but we want to keep the science target fixed on the science camera. So we want to move our wavefront sensor. So that's the next step we're taking. And we're also looking at a small scale satellite launch to do this. We're putting in a proposal for that. So, what's the future at Keck? First of all, the future, well, I don't know what the future is in the US right now, but in the Astro 2020 report, adaptive optics was really, highlighted. So number 1 priority was adaptive optics, diffraction limited adaptive optics on the 20 to 40 meter telescopes. Key capabilities that were identified were high performance AO and high contrast imaging. And then foundational activities included the pressing need to develop advanced AO systems into the optical. And so if we can be doing science in the optical when the ELTs are doing it in the near infrared, we're going to get similar spatial scales. And that could be good combined science. So we were in parallel developing the Keck Observatory's science strategic plan for where we want to be by 2035. The goals are shown on the left there, 6 strategic goals. And all the different projects associated with those goals are shown on the right in 3 categories of large, medium, and small scale projects. And it turns out about half of these need diffraction limited adaptive optics, pushing into the visible. And those are the projects on the right and the goals on the left. And the other half could benefit from ground layer adaptive optics. So we're really talking about adaptive optics all the time here. I think that's key. And we've been looking at things like adaptive secondary mirrors and working with Adoptica and TNO on those. To finish, I just want to acknowledge that projects like adaptive optics and telescopes take a lot of people. The group on the bottom there is largely the group of people working on adaptive optics at Keck right now. People at the top, I just retired but a few weeks ago. And so that was Jason Chin and I, our retirement party. So elements of Keck AO success. I think this is quite important that we have strong interactions with the science community. And our science community at Keck, maybe because we have a small community, they really feel like they own the Keck telescopes in the best possible sense. They're really engaged with it. And so they are the ones that provide us with our requirements, really what they need to accomplish scientifically, both for the AO systems and for the science instruments. And then we have good collaborations between AO groups and the science instrument groups. Of course, the funders are also key because all of this is, this is not part of our operational budget. We have to make proposals for all these items. So funders have been very generous for us. We've got excellent relationships, I think, with vendors, and we really treat them as collaborators, and that's been great. They've really helped us a lot. And then also the AO community internationally, we're able to have really good connections with people. These are hard problems, and it's great to collaborate. And then, of course, all that feeds into observatory operations. We need a good operations team that really can run these systems at their best capability. And that all then feeds back to the science community wanting more. And this is our current team members and collaborators at Keck, consultants at Caltech, UC, UH, NASA Goddard, industry partners. And so, muchas gracias. Y aloha.
Thank you very much, Peter. Any questions in the room?
Well, Peter, thank you for this talk. I think we will need some time to digest the ton of info that you have given to us. But I'm interested in the system that you use routinely to co-phase the primary mirror on Keck. Could you please develop a bit more? Because I understood that you use two different systems, or you are experimenting with different systems.
We're experimenting with different systems now, but the system we use on a routine basis, which means after segment exchanges or but once a month to phase the telescopes, is a system that was developed back in the 90s.
Right.
Which is just developed by Gary Channon and Mitch Troy in UC. And it's just an interference pattern.
Right.
Over a small aperture.
The edges.
Over the edges. And then you use then the active control system to maintain that over time. And it's a simple step of using narrower filters initially, because it's got a capture range of something like 30 microns when you're using those. And then you step to broader filters, and you're just and you're making like 11 steps of segments with respect to each other, and just correlating images. So you've got a theoretical image of what it should look like, and you're doing a correlation with the actual image, and that seems to work.
So it's quite standard. How often do you run the full process to reconfirm the co-phasing?
Every time we do a segment exchange. So we do that for half the year, once a month. We exchange 6 segments.
Right. So your system is able to maintain the co-phasing within the allotted budget for nights.
Yeah, I found that actually, if you leave it 1 month to rephase, or 3 months, the errors are the same. I don't know that they're exactly the same errors.
Yeah.
But the RMS values are about the same.
Right. Thank you.
Okay.
More question?
Thank you, Peter. Happy retirement.
Thank you.
And I'm ignorant about the adaptive optics. I will, in my opinion, in my knowledge, that right now there is no adaptive optics, right? Optical. In
the visible?
Yes.
Yeah. At visible wavelengths, the Stewart Observatory, the group, Laird Close and Jared Mayles, they have a system they put at Magellan.
Okay.
In Chile. They go down there, for some runs, right? It's not a facility, but it's a visitor instrument, and they've demonstrated science down to 500 nanometers.
So what's the difficulty to go down from infrared to optic? optical wavelength.
It's everything gets harder, right? Because you're doing it with respect to the wavelength of light, right? So as you go to shorter and shorter wavelengths, your performance has to be better. And so you need more actuators. You need a faster control system, things like that.
And how about in the mid-infrared?
Mid-infrared's easy, right? I mean, if you go to 10 microns or something, you basically, if your telescope's phased, you already get a diffraction limited image, and you can improve the Strel a little bit, but it's not hard.
Okay,
Yeah.
thank you.
Hi, Peter. I would like to ask you if changing your M2 by an adaptive secondary mirror from TNO, is it a close decision or something you're just considering as a future possibility? And has it been designed to be optimized for what wavelength, visible or infrared?
I don't know that it matters which wavelength. It's
For
basically
the
a number.
amount, I mean, for the amount of actuators.
Yes, in fact, the number of actuators isn't finalized, but it's either 2,000 or maybe as many as 4,000. And that would allow you to go into the visible. If you took 4,000, 2,000, you might probably need another stage. TNO, in a preliminary down select, TNO was selected over Adoptica for reasons of power and things like that, right? These are lower power actuators. But we don't have the money right now, right? So it's been a conceptual design with them so far, but it's not funded yet.
So you showed a plot at one stage where you were, for some of these upgrades, you were predicting an improved contrast for the Keck system compared to James Webb. I just wondered how do you do better than James Webb? Is it just a question of the mirror size, or is there some what is it that actually gives you this improved contrast predictions?
Yeah, part of it is the size of the telescope, 10 meters versus 6.5 meters. And part of it is also, I think right, I'm trying to think about this.
I don't mean to put you on the spot. I mean, I guess
No,
I was just interested in finding key science that you can do better from the ground than in space is very interesting, right?
Right.
So where can we do better from the ground?
And I think it's also taking advantage of the difference in instrumentation, right? Because we'll have higher spatial resolution as well, right? And so it's taking into account the instruments we can use, which are basically, in this case, scales. It's a 2 to 5 micron integral field spectrograph, and it has chronographic capabilities as well. So I think it's making use of that whole group of approaches.
Okay.
But it's the raw contrast. It's not using anything beyond that as well.
Okay.
Okay.
Thanks.
Thank you for the presentation. I have a question. For the development of new wavefront sensor, are you exploring to use integrated photonic technologies or photonic lantern?
Not yet, but other groups are. And particularly the Australians have demonstrated at University of Sydney, have used photonic lanterns, and then they come to multiple single mode fibers. And actually with something like a neural network, you can start to identify different modes, right? So people have started using them for some form of wavefront sensing, but I'm not aware of anyone using them in an actual system yet. There's also some really cool photonic stuff happening right now.
We are exploring some solution in this way that maybe we could talk about.
Oh, cierto. Gracias.
More questions?
I don't know if there's any questions online. Oh, gracias a ustedes. So I think you